All right, guys, here's example 1 of section 2.3. Find the points of discontinuity of, we have parts A, B, and C. Is that it? Yep, A, B, and C. All right. So the first one is y equals x plus 1 divided by x squared minus 4x plus 3. Now, before we start example A, let me just kind of tell you a quick joke, okay? What did one eye say to the other eye? So what did one eye say to the other eye? Between us, something smells. Do you know what it's talking about on your face? So between two eyes, what's in between two eyes? Your nose, and your nose can smell stuff. Ha! Get it? So find the points of discontinuity. The first thing we might want to do is see if it's factorable, especially when you see it as a rational function. On the bottom, x squared minus 4x plus 3. The two factors are, whoops, it's a minus 4 on the bottom. So x, let's see, minus 1 times the quantity of x minus 3. All right. It's factorable, but I can't really cancel, aka reduce. Therefore, you're just going to have two vertical asymptotes. And remember, the vertical asymptotes is after you reduce. Since we can't reduce, I have two. Take each factor on the bottom, set it equals to 0. So the first one is x equals to 1, and the next one is x equals to 3. So because this is a vertical asymptote, the points of discontinuity are infinite. These are called infinite discontinuities at x equals to 1 and x equals to 3. So that's what they are asking for if they are asking you to find the locations of the discontinuity. B, y equals x divided by absolute value of x. Now, as you can see, it's a rational function, sort of, right? So technically, this could be a vertical asymptote, but make sure you check to see if the definition of vertical asymptote matches with our calculus definition. So for your vertical asymptote definition, its limits as x approaches c, either from left or right, of your function should approaches or should equal to positive or negative infinity. Now, we wrote down all of the definitions of discontinuity. You also had a jump definition. The definition of a jump is as the limit approaches c from the left or right of your function, it equals, okay, it has an answer. So that means it has a finite answer, but they are not the same from the left and the right. So when you think you have a VA, double check to make sure if it's not a jump. So what we want to do is the point, okay, the point of issue or problem, it's really at x equals to 0. So you want to check it out. So limit as x approaches 0 from the right of x divided by absolute value of x. This should be 1. Now check to see at x approaches 0 from the left of the same function. This should be negative 1. So as you can see, you have a finite answer. They are not the same. So the discontinuity location, this is a jump at x equals to 0. Okay. Last example of last part of example 1 is letter C. So this is a piece y equals, the first piece is 3x minus 1 when x is bigger than 0. The second piece is negative e to the x when x is less than 0. So as you can see, because neither piece is including 0, So really the issue or the problem, again, it's at x equals to 0. So, oops, that's a lot of equal sign. There you go. So you want to do your limit test to see what type of discontinuity it is. Okay. So the limit as x approaches 0 from the right side and versus the limit as x approaches 0 from the left side. Now, because it's a piecewise, you got to pick the correct piece. If you're approaching 0 from the right side, it has to come from the first piece. Now, I can use substitution right away. So when I plug in substitution of 0, 3 times 0 minus 1 is a negative 1. Now, if I'm approaching 0 from the left, I am now using negative e to the x. By substitution, e to the 0 power is now going to be 1. 1 times the negative 1 in the front is now negative 1. Now, since the left and right limits, they exist and they give you a finite answer, okay, as you can see, whoops, they give you a finite answer, right? So we know already it's definitely not an infinite, which is a VA. So we know it's not a VA. We know it's not a jump because left and right are exactly the same, okay? Now, if you think about it, it's not oscillation because we can find the limit pretty easily. So it has to be a whole. Okay, now why is it a whole? Because the whole definition is that the limit as x approaches 0 of your function exists, okay, which it does, but not equal to f of 0. Well, we don't even have an algebra value of f of 0 because you can see the notation, none of this has an equal sign on the bottom. So that's why f of 0, the algebra part of it, is not there. But the limit exists at 0. So therefore, class, this is called a whole. A whole, aka a removable at x equals to be a 0. Okay, so let's just recap really quickly. Oscillation is a type of discontinuity. A whole is a removable when the limits exist, but it does not equal to its algebra value. You're going to have also the jump. The jump is the left and right limits. They exist, they just don't equal to each other. You also have VAs, aka infinite discontinuities, which is when it does not is not reducible when you factor it out. So those are called VAs, right? When the limit approaches at x approaches, in this case 1 or 3 from the right or left side, y is approaching either positive or negative infinity. And that's the last component of example number 1.